concurrency-aware object-oriented
This on
programming
your
with
belt
roles.
and this near your
This
belly.
is a neat paper because it allows you to describe concurrent programming in a model that is safe, but also remarkably simple from my perspective. So Michael Pace will be giving the talk, which is joined with Tomas Gross. Thank you very much. Right, so concurrency-aware object-oriented programming with roles. So we're talking about a model for concurrency. And I'm sure you all know a very simple model for concurrency, which is the thread-based model. So in an object-oriented world, the thread-based model looks like this. We have a thread of execution. And when methods are called, then the thread kind of switches from object to object and can access whatever object state the thread is currently in. Now, of course, if we have multiple threads that happen to have access to the same objects at a particular point in time, then we get into trouble. So we can have concurrency bugs like data races, or if we try to fix them with logs, we may run into deadlock. So this model is maybe not the simplest one to program with. So we have heard about actors today. Actors try to address this issue by kind of splitting up the program into isolated parts. And in each part, there's only one thread running. So the only way to communicate is by sending messages. So when we compare these two models in terms of relation between threads and objects or data, we see that in a thread-based model, there's no real strict relation that we can look at between threads and objects. And on the other hand, in the actor model, we have a very strict relation. In fact, for every object, there's exactly one thread that can access it. Or you could even go as far as saying that the objects are the concurrent entities themselves. So in this work, we wanted to design a model that is similar to the thread-based one, because we think it's in principle simple and widely known, but with guarantees provided by actors, or as we will see, maybe even better. And the idea is to make the relationship between threads and objects explicit. And we call this relationship roles. And roles, what the roles do, they define which thread has access to which object. So every object plays a role in every thread that is currently active. So we call this model concurrency-aware, and I'm trying to explain you why. So when we have only one thread in the system, the blue thread here, then this thread has access to all the objects. And when the thread starts another thread, it explicitly shares some objects with this other thread, and these objects then react by changing their roles. So whenever an object is shared with another thread, it adapts to the new sharing pattern by changing the roles, and therefore by changing the possible accesses that a thread may do. So what are the advantages of such a model? We think this may be very accessible to programmers that are familiar with threads. It is potentially very efficient on shared memory because you don't have to copy mutable objects to which you may have to do if you had an actors-like model. And most importantly, the model, as we presented, is deterministic by default. And this means that any parallel execution of a program that follows this model is actually guaranteed to produce the same result as if the program was executed in a sequential way. So this is obviously a very strong guarantee. So the contributions of this work is the model itself, including a formal proof that it is in fact deterministic. We also present the design of a language that enforces this model. So every program written in this language is actually guaranteed to produce these sequential results. And we have a prototype implementation of this language that we submitted as an artifact, and that is available on GitHub. And finally, we also have some empirical evidence that we can get some performance out of this, which is, of course, what we want to achieve when we're talking about parallel programming. So let me give you some details about this programming model. As we've already seen, we have two kinds of entities. We have objects and we have tasks. You can think of these as threads, but we use them on a higher level, so we call them tasks. And objects, as you might expect, they contain fields and methods. And, of course, the new thing, that they contain roles. And they contain one role for every thread that is in, for every task that is there. And this role defines whether a task can access the object, and if so, in what way. So the model is, we claim this model is really simple. We have only 3 different roles. We have the read-write role that gives a task full access to the object. So it can read and can write. Then we have the read-only role that restricts it to reading from the object. And finally, we have a pure role, which you can think about as kind of inaccessible. So a task cannot access a pure object except for final fields, which are always safe to read because, yeah, they don't change. And we use the following notion here in this talk. So we use a symbol together with a color. The symbol means the role, and the color indicates the task that this role is played for. So the blue pen, for example, means read-write role in the blue task, or a purple eye means the read-only role in a purple task. So the model, the interesting part of the model is about when roles change. And there are some strict rules about this. And I'm going to explain these rules with some code snippets that are written in the language that we present, which is called roles. So the language is very similar to Java. You have methods, you have classes. And what you have in addition is tasks that you start by using the start keyword. And what is special about tasks, they have to declare all the objects that are supposed to be shared with this task explicitly as a parameter. And in addition, they have to declare the role that this object is supposed to play. So here in this case, we have one single parameter, an account object, and this account object is supposed to play the read-only role. And if so, then in this compute interest task, we can access this object in a reading way, but we cannot modify it. So when we execute this, when an object is created, then it plays, as a rule, it plays the read-write role in the task that creates it. So in the beginning, it's read-write for the blue task. And then once this task shares it with the purple task that requests it to be read-only, then the object changes its roles, and it changes the roles in both tasks. This is the important part, basically. So now it's read-only in the purple task as requested, but it's also read-only in the blue task for now. And this means that the 2 tasks can basically not interfere because both can only read from the object. And then once the purple task is finished, the object is released, and it switches back to its original role, which is read-write for the blue task. Now, if we change the example a little bit, we say this task needs a read-write access instead of read-only. A different role transition happens. So in the beginning, the object is read-write, as before, for the blue task. And then when the blue task shares it with the red task, it changes, the object changes its roles. It becomes read-write in the red task, as requested, and it becomes pure, so inaccessible, basically, in the blue task. And again, this means that there cannot be any interference between the 2 tasks. And once the red task finishes, the object switches back to read-write in the blue task. So the last ingredient that we need to understand how this model is in fact deterministic is something that we call guarding. So when we look at this example again with the read-only parameter, as we saw before, when we share this object with the purple task, it becomes read-only in both tasks. And now, of course, the blue task continues execution. And when it tries to read from this object, that is fine. That is allowed by the read-only role. But once it tries to write to this object, well, the question is what happens now, right? Do we simply throw an exception or something like this? This would be a bad idea because this depends on the progress of the purple task. So instead, what we do is we stop the blue task temporarily using something that we call a guard. And the guard basically delays the blue task until the purple task has finished. The object has switched back to the read-write role for the blue task. And now this operation is in fact legal and can be executed without any problem. And now we can understand how we can determine guarantee determinism. If we have two tasks and there's no interference between them, they can just execute in parallel and nothing bad can happen. On the other hand, if we have two tasks and there's interference between them, then the parent task, so the original task that started the other task, is delayed until the child task has finished, and then the operation can succeed. And we call this child task priority. So the child task will always be the one that can continue to execute while the parent task will have to wait. And what this means is that here you can see that this really in the extreme case, when the blue task has to guard right away, it reverts back to sequential execution, right? This is the same as if the blue task had just executed all the code by itself by calling a method instead of starting a task. So this is basically how the model can guarantee determinism. As long as there's no interference, we can execute in parallel, and as soon as there is some interference, we revert to sequential execution. So let me show you one language feature that is kind of important. There are more in the paper. And this is about data parallelism. So the question is, how can we process an array of data in parallel? That means with multiple tasks. Well, if the data is read-only, this is fine. We can just share the array with multiple tasks. This is possible by these role transition rules. But what if we want to write to the array from multiple tasks? We cannot share them as read-write, or we cannot share the array as read-write, because this would allow the tasks to interfere, possibly. So instead, what the language provides is something called slicing. And with slicing, the programmer can kind of split the array into different parts. For example, one part that covers the first couple of elements, and then another part that covers the rest. And this can be done very efficiently because slices, they're not actually splitting up the array, but instead they're just views on the array. They are views, so they refer to the same underlying data, but they only allow access to some of the elements. And in fact, the array itself can be considered a slice that covers the whole array. So we can do this efficiently. Now, what does it mean in terms of roles when we have slices? So if we have two slices here, 1 and 2, and we share one of the slices with another task, what happens is that so we model this in a way that every element plays its own role. And only the elements that are covered by the slice are affected by this sharing, right? So the roles of slice 2 are unaffected, and this means that slice 2 can be actually used and shared independently. And this is how we can get efficient data parallelism with this model. And in the code, this could look like this. We have an array of account objects. And on this array, we can call a built-in method that is called partition, which takes a partitioning scheme as an argument and the number of partitions. And what we get back is basically an array of slices. So we get back 4 slices, and we can share each of these slices with one task, and then every task has access to its own slice, and nothing bad can happen, basically. So as you have seen, this model is based on some runtime checking. So the question is, what do we pay for this? What do we pay for this simplicity and for this safety? And to find this out, we implemented roles using a source-to-source compiler to Java, and we implemented a couple of programs in this language, and also in Java to compare the performance of the two languages, so to say. So what we show here is the speed up, and on the x-axis we have a number of tasks or threads that we use to execute the program. And on the y-axis, we have the speed up. And the speed up is relative to a single-threaded Java execution. So we compare both roles and Java to single-threaded Java execution, that we can see the overheads that we get. And we actually have two lines here, but in this particular plot, you cannot really distinguish them very well. The blue one corresponds to roles, and the gray one that is kind of hidden behind corresponds to the Java implementations. So we have a couple of different programs here, different results. We can see that for some programs, roles indeed has some overhead. So this is a n-body implementation, and you can see the blue line is clearly below the gray line. So we see that roles doesn't perform as well as Java in this case. But for other applications, we get some very decent performance. For example, here we get a 25 times speed up for both roles and Java on a 32-core machine. And across the board, we see that we can actually get speed ups for all the applications if we have enough tasks available. So to conclude, we have looked at the thread-based model and at the actor model, and at this new model that we're proposing, which is kind of a hybrid between them or in between them. And we argue that this concurrency-aware model is actually a viable option, especially to do parallel programming on a single machine when we don't have any distribution going on. And the reason is because it's similar to the thread-based model that many programmers know. It gives you some very strong guarantees. It's deterministic by default. And as we've seen, we can get some decent performance out of it. And if you're interested, talk to me. I'm here for the rest of the conference. Or you can also try this out. It's available on GitHub. And with this, I'm done, and I'm happy for questions.
All right. Questions from the audience?
Thanks. Interesting talk. I have a kind of language design question. So this model with roles that you have, it kind of reminds me of a sort of dynamic version of ownership and borrowing in Rust.
Exactly.
So I was wondering, do you think there's an advantage to doing this dynamically, or was there a technical reason why you do it dynamically instead of sort of making this explicit in your source codes, basically?
Right. So the advantage is that it's much simpler, I would say. In Rust, or also there are other languages that try to get the same guarantees statically, right? For example, there's deterministic parallel Java, there's permission systems, there's Rust. All these languages have to deal with aliasing in the compiler. And in this model, you really just declare the roles, and all the interference checks happen at runtime. So you can have any aliasing in your program, and it's really unrestricted. And of course, you pay for this simplicity, possibly with some runtime overhead. So it's a trade-off between simplicity and performance in a way. Yes.
Yeah, so nice talk. I was wondering, what about nested data structures, like tree structures? If I send that, do roles apply transitively?
Yes.
And if so, can you, how would you model parallel access to a tree structure?
Right, so this is a good question. So the language, actually, when you share a data structure with a task, the data structure is shared transitively, right? So if you share, and then if you have a tree, for example, you can easily share one subtree with one task and another subtree with another task. And as long as you don't have any back references, this would be fine. Other questions?
Philip?
Thanks for the interesting talk. I have also a question that's related to the previous one, which is once you share an object with another task, you need to update the roles, right?
Yes.
And but is it possible that you have to update the roles in a big object graph? right? Where you're not just like for one object you have to update the things, and if so, what is the performance impact? Second question is, you mentioned aliasing, like can you transfer object graphs where you have internal aliases? And then I think I have a third question, which is that the model you presented is basically task and data parallelism, right? So I wonder if you can have sort of cycles in your dependency graphs. Thanks.
All right, so first question. Yes, if you, so you have to be careful to design your data structures or your program to not like refer to the whole heap or something, because then you will just share your whole heap, which is bad for performance and also bad for parallelism. So this is something that that you have to be careful about. We have some mechanisms that I could not talk about today, where you can actually not only slice arrays, but also objects to be able to share only a part of an object and not some other part. So this is one way to address this issue. And then, what was the second question? Internal aliasing, right. So the model as it is now, or the language as it is now, if you have, it's very simple. It's basically an object, an ownership model where just, if you have a reference to an object, you own it, right? So if you share an object, you share everything that it has a reference to. But I could imagine that this could be combined with some ownership notion that makes this explicit, and then only shares objects that are actually owned by such an object. And the third question,
Cyclic dependencies.
Cyclic dependencies among tasks. Yes, so we don't support this yet, or we don't support this. So we have a clear hierarchical task structure, and this is also the reason why we don't have any deadlock problems, right? Because only the child, you can only ever wait for child tasks, and once this child task has finished, you can go on.
Okay.
So I'm thinking of a structure as simple as an array list.
Sorry?
I said I'm thinking of a structure as simple as, say, an array list. And I get that we could, slice it up, provide some sort of interface for you get this part of the list, you get that part.
Yes.
And that could happen recursively. And for each of these delegations, right, this task gets this piece, it seems like I'm going to have this nice chain of notes about which task has what permission to that chunk of the array. So if I have an array list of ints, it seems that if I'm not careful, very quickly, the amount of information I'm storing for who is allowed to access what vastly outstrips the size of the data element in that slot of the array itself. I suppose my question is, did you do any tests in terms of memory consumption? And was that impacted by this sort of like recursive splitting?
So if I understand the question correctly, you're wondering about the overhead of keeping track of which task has access to which objects. So in the case of slices, we don't actually keep track of every element's role. So this will be rather inefficient, but instead we keep track of only the roles that the slices play. And we keep track of of which slices overlap with other slices. So basically, if you do some reasonable slicing without overlap, then you don't have a lot of I should say overhead. Yeah, let's say.
Okay, last question.
So I'm wondering about concurrent assignments to roles. So consider a case where there are two concurrent tasks. Both are spawning tasks which claim for a write access to the same object. Then depending on which you reclaim first, the behavior might change, right?
Yeah, so this is not possible. If you have two concurrent tasks, and one of them has write access, it's impossible that another one has write access at the same time. Mm-hmm. And if they don't have write access, they cannot give write access to other tasks.
Okay, so spawn and the accesses are also, these accesses are also tracked, and
yes,
they can't claim at the same time.
So basically, if a task doesn't have write access, a task can only give another task as much access as it has itself. Yeah.
I see. Thanks.
Okay. All right. Invite everyone to stay here for the for the next session, which is the awards, and also at SIGPlan Town Hall, and then go to the poster session and the student research competition. But before we do that, let's thank Michael Face and all the speakers.